Okay, let's move on to the last chapter, which deals with shorelines and the ocean. Now, the land meets the sea along broad regions that are called coasts, and the line where the water surface intersects the shore is the shoreline. Shorelines, in turn, are shaped and sculptured through the action of waves and tides. Here we can just see that there are many different types of beaches around the world. For example, some beaches consist of clean quartz sand, as for an example, Galveston, the beaches along the Gulf Coast. Well, I probably wouldn't want to call it exactly clean sand, but sand nonetheless. Other beaches, where particularly when there's a lot of abrasion and reworking by strong waves, may consist of nothing more than smooth, rounded rocks. There's a beach along the Florida Sanibel Island consisting entirely of shells and shell fragments. If these shell fragments were cemented together by calcite, what kind of a rock would we get? Coquina. Yeah, coquina. And to the right, we have a photograph of black sands on the beach of Hawaii because these particles were derived from weathering of nearby basaltic lava flows. But we can distinguish different parts of a coastal area, beginning with the offshore zone, which occurs seaward of the coast. And from there we have the near shore, which lies between the low tide shoreline and the point where waves break at low tide. The foreshore is the area exposed at low tide and flooded at high tide. And further inland we have the back shore, which is landward of the high tide shoreline. We can define the berm. Berms are relatively flat platforms that mark the change in slope of a beach. And finally, we have the backshore dunes that form from beach sands that are blown back by incoming offshore winds. So backshore dunes are actually wind deposits rather than having been affected by waves and currents. Here, for an example, are the Galveston backshore dunes and what's known as the vegetation line. We'll find that the vegetation line is quite important, particularly when it comes to the Texas Open Beaches Act. We'll look at this in more detail as we go along. But first of all, let's look at waves. Waves are created by the wind blowing over the surface of the water. And we can define several characteristics of the waves. For example, the parts of the wave include the crest, which is simply the top of the wave, and the trough, which is the low area that occurs between the crests. We can also make several measurements of the wave. For example, the wave height is simply the vertical distance between the trough and adjacent crest. The wave length, in turn, is the horizontal distance between the crests, and the wave period is the time interval between the passage of two successive crests. The height, the wave length, and also the period of the wave depends on several factors that include the overall wind speed, the length of time that the wind has blown, and also what's known as the fetch. Fetch is simply the distance that the wind has traveled across open water. Now, although waves travel, the water mostly stays in the same place. And this can be aptly illustrated by a boat that rides up the crest and drops down to the trough of an adjacent wave. The overall, although the boat has moved up and down, the overall return position of the boat pretty much is the same position. And as a result, this demonstrates that water particles actually rotate in the circular motion, returning to more or less the same place where the motion began. As such, we can view the water particles as moving in circular motion at the surface. And what's more, notice that the circular motion of water particles decreases with depth and becomes negligible below a depth equal to about 1/2 the wavelength. Once we get below half a wavelength, deeper levels are, for the most part, not affected to any great extent by the passing waves. Now, waves traveling away from a storm center will evolve into broad, rounded waves that are called swells. And from there, swells become higher as they approach the shoreline. What happens here is that the wave base begins to drag on the shallowing seafloor. And from there, the dragging on the shallowing seafloor causes the wave to slow down, increase in height, and also become more closely spaced further and further towards shore. Eventually, close to shore, the waves will evolve into sharp-crested features that are called breakers. And from there, the breakers will roll forward into a foamy, bubbly surface called the surf along the surf zone. And from there, the waves wash up, run up onto the beach as swash, and run back down as a backwash. I bet you never really noticed this at Galveston. Well, next time you're on the beach, you could be amazed by all these changes in incoming waves.
Trust us, there's very little to be amazed.
Pardon?
There's very little to be amazed.
Yeah. Anyway, here's a photograph of breakers and surf off the former flagship hotel, Galveston Island. Unfortunately, Hurricane Ike a few years ago pretty much did away with the flagship hotel. Today we have that pier amusement park that occurs in its place. Now, a rip current is a concentrated movement of water flow opposite the direction of breaking waves. As for an example shown in this photograph, notice that in this area outlined by the red dashed line and indicated by the red arrow, the rip current actually extends outward from the shore and interferes with incoming waves. So these things are fairly easy to spot, particularly if you're on the beach with strong incoming surfs. What happens, rip currents by definition are simply narrow currents that flow straight out to sea along the surf zone. And they're fed by mainly water within the surf zone where the backflow is the water that's flowing back out into sea. Within the rip currents, the backflow becomes localized and are basically located where waves in the surf zone break early due to the underwater channels or as a result of these wave interference patterns. But the backflow quickly dies out with depth, ending just outside the surf zone. So if you're offshore wading through the water and get caught up in a rip current, the last thing you want to do is walk parallel with the rip current. Instead, you want to walk at 90 degrees to the rip current, parallel to the shoreline. Now we can also look at what's called wave refraction. As waves approach the beach, the rows of waves will then bend in a direction more parallel to the shore, and this is what's referred to as wave refraction. What's happening here is that the end nearest the shore encounters the shallow water first and slows down, while the end further from shore is moving faster and will eventually catch up with the near shore end, causing the overall wave to bend parallel with the coastline. So by the time the wave crests reach the coastline, notice that the crests are almost parallel with the beach. Okay. What's more, wave refraction will cause waves to diverge within coves. In other words, the waves will spread out when entering coves, and this in turn minimizes impact resulting from net deposition of beach sediment. So notice within this illustration, this block diagram, that the beach deposits are occurring within the coves as a result of the minimal impact within these areas. On the other hand, the headland, which projects out into the water, the headlands do not have a beach. And that's because waves converging at headlands are maximizing their impact and as such are eroding the coast. Okay? Now, even though wave refraction results in near parallel alignment of the waves with the beach, the waves will still approach the shore at a slight angle. And as a result, the waves wash up and back on the beach, causing grains on the beach to move down beach in kind of a zigzag pattern, which is referred to as a longshore drift or simply beach drift. This slight encroachment of the waves at an angle will also generate a longshore current offshore that parallels the coast. The net result is that we have net sand movement down beach, both onshore and a little bit offshore. Okay? Yeah. It's simply the waves washing up and back on the beach will cause the grains on the beach to move in a zigzag pattern down beach. And this is what's called a longshore drift or a beach drift. If you're going on the Galveston field trip, we'll actually go on the beach and watch this happening with the waves washing back and forth. It's actually quite cool. Okay. And here's another example. Notice that the path of the sand particles on the beach are in the zigzag pattern, and the overall movement of the sand on the beach is in the down beach direction. And we also have offshore current, the longshore current, a little bit offshore, that's also transporting sand in the same direction. Okay. So let's move on to tides. The sea rises and falls twice daily along many coastlines. There are times of the day where high tide occurs, and in this case the boats are floating. But then several hours later, low tide sets in and the boats are sitting on dry land. What exactly causes the tides? Well, the tides result from the moon's gravitational pull on the Earth, creating what are called tidal bulges. And notice that tidal bulges occur on two sides of the Earth, on opposite sides. The one tidal bulge faces the moon, and is the result of the moon's gravitational attraction on the Earth. The second tidal bulge occurs on the opposite side, and this is because the moon's gravitational attraction is least along this side of the Earth. And these bulges are occurring in the oceans, not on land. We don't see the bulges on land. Now what's happening is that as the Earth rotates once every 24 hours, high tide occurs when the coastline passes under one bulge. And from there, several hours later, low tide will occur when the coastline is between bulges. And the second tide, high tide of the day, will occur when the coastline passes under the second tidal bulge. Okay? Everybody see this? Ready? Well, we don't technically actually see this in the classroom, but and so along any given coastline, we'll have a low tide shoreline and a high tide shoreline. However, if we stand there and watch the tides change on a day-to-day basis, we'll notice over several days to weeks that the maximum height of the high tide can vary throughout the month. For example, the whole low tide shoreline and the high tide shoreline, there are times of the month when the high tide shoreline is higher, and other times when the high tide shoreline is lower than average. And this is the result of what are called spring tides and also neap tides. Highest tides are the spring tides when the Earth, Moon, and the Sun are aligned. How long does it take the Moon to orbit around the Earth? Yeah, roughly 1 month. And so during that 1 month period, we'll get a new moon, full moon, and things of that nature. Highest tides are the spring tides when the Earth, Moon, and Sun are aligned, and this occurs twice a month. During the new moon, when the moon occurs between the Earth and the Sun, and the full moon, when the moon occurs behind the Earth. Now, during these times, when the moon is in full or new moon position, the tidal bulges created by the gravitational attraction of the Sun and the gravitational attraction of the moon become aligned, and this is when the overall tidal bulges are the largest. In other words, we have the juxtaposition of both the solar bulge and the lunar bulge, creating a maximum bulge during these times of the month. Okay? The lowest tides, on the other hand, are the neap tides, when the moon and the sun occur at right angles. Now, when the moon is in the first or third quarter position, notice that the tidal bulges produced by the moon are at right angles to the bulges created by the sun, and as a result, the overall tidal range tends to be smaller. The overall bulges, on the other hand, are quite a bit smaller. Now, there's an actual video of this. It'll be posted in the learning module for this chapter. Now, even though tides occur twice daily along many coastlines, the tidal patterns and occurrences can be quite different for different coastlines. For example, some coastlines exhibit what's called a mixed tidal pattern, as indicated by the blue color along, for example, the Pacific coast and parts of the east coast of Canada. Mixed tidal patterns is when there are 2 high tides and 2 low tides within a 24-hour period, except that the high tides and low tides are of unequal heights during each tidal day. Semi-diurnal tidal patterns is when 2 high tides and 2 low tides occur at approximately equal heights during each tidal day. And those are outlined by the coastlines appearing in red, mainly along the coastlines facing the Atlantic Ocean. There's also what's called the diurnal tidal pattern, where we get just 1 high tide and 1 low tide each tidal day. And a diurnal pattern tends to occur along parts of the Gulf Coast that are color-coded green. So the overall height or time of the actual tides are influenced by such things as the coastline shape, the overall configuration of the coastal ocean basin, and also the water depth near the shore. Also, what's shown in this figure are the total spring tidal ranges. Notice that the spring tidal ranges along some coastlines, basically the difference between high and low tide during spring tide, tend to be quite large, in excess of 2 meters. And those mainly occur along the coastlines facing the Atlantic Ocean and also along the Pacific coast, where the spring tidal range is in excess of 2 meters. On the other hand, the Gulf Coast has a very low spring tidal range of about only half a meter, maybe 0.7 meters at the most. So our part of the Gulf Coast is what's considered a microtidal range of significantly less than 1 meter. Now, tidal flats are simply the muddy and sandy areas that lie above and are exposed at low tide but are flooded at high tide. Some coastal areas, particularly the coast of France, has very large tidal ranges, and so this entire tidal flat shown in the photograph will be completely covered by water within the next few hours, except for the parking lot, which I assume will not be flooded since cars are parked. Anyway. Shore features depend on such things as the overall composition of rock or sediment, whether the coast is stable, shrinking, or rising. It can also be affected by currents and the overall intensity of waves. As a result, the shore features tend to vary dramatically from one place to another. Let's first of all look at what are called depositional features. These are features related to beach drift and longshore current, resulting mainly from the deposition of sediment. And they include such features as spits, baymouth bars, tombolos, and barrier islands. A spit is simply a ridge of sand that projects from land into the mouth of an adjacent bay. Barrier islands, for quite a few barrier islands, tend to get these projections of beach into an adjacent bay or cove. In this aerial photograph, we see a spit over towards the right, which extends into an adjacent bay. And notice that the spit will then bend inward towards the bay. And this is because of the encroaching waves. The beach drift and the longshore current is actually responsible for the extension of the beach offshore to form a spit. But then you also have these incoming waves which literally push that extension inward into the adjacent cove. And as a result, spits often bend into the cove the further they go offshore. On the other hand, further up in this upper part of the diagram, we have what's called a baymouth bar. A baymouth bar is simply a ridge of sand that completely crosses the bay, closing it off from the ocean. Of course, we can get little breaches in the baymouth bar in what are called tidal inlets. And these in turn can produce these little tidal deltas that we'll look at in a little bit more detail. Here again, notice the direction of the longshore current. This is the direction that the beach sands are traveling. Here we see a baymouth bar where the beach sands have crossed the cove, blocking it off from the ocean. And also notice that further over towards the right we have a spit that's extending offshore. And the spit is projecting offshore in the same direction that the longshore current is flowing. This tells us the overall direction of the beach drift and the offshore sands. And as I mentioned before, notice how the spit bends inward into the cove. This is because we also have incoming waves that push that sand inland, causing that inward bend in the spit. Do you see that? Okay. A tombolo is a ridge of sand that connects an island to a mainland. Here, for example, we see an offshore stack, sea stack, which is connected to the main beach by a ridge of sand. It probably will not make any noise if you blow into it, though. Not like a trombone, but that's a bad joke too. Forget. Barrier islands are long sandbars that are not connected to onshore beaches, mainly constructed by longshore currents, and tend to be common along stable continental margins. Here, for an example, is a photograph of barrier islands that are separating the Gulf of Mexico from mainland western Florida. And of course, the best example of a barrier island is Galveston, Texas, which is completely separated from the mainland by an intervening lagoon. Now, there are different characteristics of barrier islands depending upon whether we're considering the seaward side or the lagoon side. On the seaward side, here we have high energy wave and current action from the Gulf or the ocean or whatever, whereas on the lagoon side, this side is quite a bit quieter, of lower energy. There could occasionally be storm washover deposits, but for the most part, it's a quieter, lower energy type of environment. On the seaward side, the shoreline is fairly straight because of the high energy and current action, whereas the lagoon side is quite irregular. On the seaward side, the sand on the beach is typically clean, well sorted, and rounded with ripples and cross bedding. Again, it's because of the high energy wave and current action. Whereas on the lagoon side, we typically get tidal marsh muds and peat deposits. And here's a pretty good photograph showing the distinct difference between the very straight shoreline on the seaward side versus the irregular, muddy type of shoreline on the lagoon side. The landward side, the lagoon side, Typically is characterized by lagoonal mud deposits. We could get tidal delta sand, storm washover deposits, but mainly we find tidal marsh mud and peat deposits and things of that nature. Salt grass tends to be very common on the lagoon side, whereas on the beach side, facing the Gulf or the ocean, we mainly get very clean beach sands. Here's some features on the lagoon side of Galveston Island. Salt marshes, open bay, algal mats, things of that nature. Tidal deltas, in turn, are created by currents that flow through inlets in response to either tidal cycles and or overall wind patterns. There are actually two different deltas associated with these breaches. Flood deltas are deposited landward of the inlet, such as within the lagoon behind the barrier island, whereas the ebb deltas are deposited on the seaward side of the inlet. A good example of a tidal delta is San Luis Pass off of West Galveston Island, which is actually a tidal inlet. And so here we're seeing in the bottom photographs the western edge of Galveston Island, and then we also have Follett Island on the other side. But if you look closely at these photographs, notice that we can distinguish a flood tidal delta, which is deposited when Gulf water flows into the lagoon. And we can also distinguish an ebb tidal delta, which is deposited when the lagoon waters flow out into the Gulf. And if you go on the Galveston Island field trip, we're going to cross that toll bridge between West Galveston Island over San Luis Pass. And if we look at both sides of the toll bridge, we should be able to distinguish the flood tidal from the ebb tidal delta. On the Gulf side, the ebb tidal delta can only really be seen as the position where the waters break. But otherwise, the sediment is mainly underwater. Any questions on this? It's remarkable what waves and currents can do to sand. Well, actually, let's see. Hey, it's our favorite slide. Lecture's over.